Good morning, everyone. Welcome to our second session in Student Revision Series. And in this session, we'll concentrate on complex numbers, and it is part 1. Another session on complex numbers will be on Monday. So what we'll look at basic operations with complex numbers, geometrical interpretation in the Argand diagram, solving equations over C, factorizing, and also discuss conjugate root theorem and the implications. So let's start with our first example. We are given Z1 is 2 plus 3i and Z2 is p minus 6i, where p is a real number. We wish to find Z1, Z2 conjugate in terms of P, and then the value of P such that Z1, Z2 conjugate is a real number. So let's go to the calculator. This is the question. So I will enter the calculator screen, and I will type 2 plus 3, and remember that we need to access I from pressing the pi button, and we'll close the bracket, and we multiply it times our second number, where we have p minus 6, and again we need to get I from here. So the calculator will perform operations, of course, in any setting. I'm in the real setting now. I'll talk more about settings later. And it is a CAS calculator, so we can use a pronumeral. Now, our question was then asking, find the value of P such that this product is a real number. What does that mean? That means that the imaginary part of this number needs to be equal to 0. So if we go to menu and number, and we go to complex number tool, we have the imaginary part there. If I press the up button and enter, then I get the imaginary part, and if I press enter again, the calculator just gives me the imaginary part of this product. And of course, then I can use solve this equation for P. I know you can solve without. We want this part to be equal to 0, and we're solving for P. So that is the answer, P equals 4 for our first question. Second question is a multiple choice question. We multiply a non-zero complex number by this quotient, 1 minus I over 1 plus I, and then it will result in a rotation about the origin on the Argand diagram. The question is, which one is the rotation? So firstly, we need to find out what this number is. So again, I go to the calculator screen, and I will use the fraction tool 1 minus, and now we need to use I over 1 plus I. So clearly we see that we get times -1. So what happens if the complex number gets multiplied times minus I? You can try with numbers, as is done here. 4 plus I times minus I is 1 minus 4i. And if I plot those two complex numbers on Argand diagram, I can see it rotates 90 degrees clockwise. Therefore, the answer to this question will be B. Next question is, let Z be a complex number such that Z squared equals minus I times Z conjugate, which of the following is a possible value for z. So this time we'll take a slightly different approach. Again, we need to be in the calculator screen, and I will just say let z be in general x plus y times I, and enter. So now the calculator remembers that z equals x plus y I. What I can do now, if you look at your variables, you will see that z actually appears there, and it will come bold. So if I say now z squared equals, and we have negative I, that's what the equation was, and it was times z conjugate. So again, you can remember that this is just C, O, and J, and then it changes from italic, that's the recognized function, and again z. So that gives me this equation. Now what I can do, I can go menu algebra solve, and I wish to solve this equation, and I, let's say, comma x. So I get a series of solutions here. If I go up and scroll to the right, I can see that one of the solutions is x is root 3 on 2y is minus a half. So I need to go back here, root 3 on 2 minus a half. Therefore, the answer to this question will be C. So notice that I can solve here the equation I obtained using just algebra solve. I do not need to use C solve because we are solving for x and y, and the calculator it quotes real parts and it quotes imaginary parts, so C solve is not necessary. But if you do use C solve, it will also work for you. Another question, typical multiple choice question, is the sum and the product of the roots of the complex equation here. So let's get a calculator screen again. And this time we would need to use algebra, and we need to scroll down to complex numbers. And what I will use zeros. So I need to type the equation. So the equation was z cubed. We need to go down here, minus 3z squared plus 4z and minus 12, and my variable is z. So that's the syntax. So the calculator gives me zeros. Now I need to find the sum of the zeros, so I can just type sum and open the bracket, and if I go up and bring it down, I get that the sum of the zeros is 3. Similarly, you can type product, or product can be also found in the catalog. So again, I want the product of those, which gives me 12. So the sum is 3 and the product is 12. So the answer to this question is E, 3 and 12. So using C zeros for sum and product is a more convenient form because I can find sum and product by using the listed zeros here. Another typical question is that we are given a polynomial. This time it's a cubic, and there is one pronumeral there, and we wish to find the value of A. So let's get another calculator screen, and this time I will define this polynomial by going menu, actions, define. That's another way of defining, and I will say P in Z equals, and the polynomial here is Z cubed plus a, and remember whenever you have a pronumerals, put always times z squared minus 7z and plus 15. So I have defined this polynomial. Now I can find now, again, as you see, I have p, and I know that polynomial in 2 plus I is 0. So I can say p into I is 0, and now again I can solve that by equating this expression to 0. So if I go up and then bring it down and I say equals 0, and this time I wish to solve for a, so I get a equals -1, which is answer A here. So defining the polynomial is a good way of doing questions if that's extended response and you need to use it a few times for other questions. When you defined it, you can use it multiple times. Factorizing. We have a quadratic here, the quadratic which does not have real coefficients. It has a complex coefficient, z squared plus 4iz plus 5. So of course it will not factorize using algebra factor. We need to again use the calculator screen, and this time we'll go menu, algebra, and if we scroll to our complex, we can see that we have C factor. So if we wish to factorize over z, we need to use C factor. So we go z squared plus 4i times z plus 5. That was our quadratic. And you need to say that the variable is z. So enter, and we have this quadratic factorized. Again, remember that our quadratic has the complex coefficient. So as we see, we have two roots, z is I and z is minus 5i, and they are not complex conjugates of each other because the coefficients are not real. Similar question here, but a bit harder. It is given that 2 plus I is a root of this polynomial, but we know that m and n are real. So this time we have a cubic with real coefficients. And we wish to factorize p in z over real numbers. So if 2 plus I is a root of this cubic, 2 minus I, of course, will be as root as well because the coefficients are real. So let's see how we can do this question. I will again define my polynomial. The other way of doing that is p in z, and you can do a sign. So that's another way, either menu action define or p in z equals, and we'll define this polynomial as z cubed plus m times z squared plus n times, here z times is very important because otherwise it would treat it as nz, and then we have plus 20. So this polynomial is defined. Now again I can find p in 2 plus I, and I can find p in 2 minus I, because as we know, both of those are the roots of this polynomial. Now, if they are the roots, that means that, of course, those expressions need to be 0. What we do now, we can actually use menu, algebra, solve system of equations, and our variables are m and n. So I can go up and bring this one down and equate it to 0. And here you can go up and do Control-C on your calculator and bring it down here, Control-V, and we also equate it to 0. So I can just use solve again because I'm solving for m and n and they are real numbers. So what I can do now, I can say, okay, so what is my polynomial for those two values of m and n? So I go up. So my polynomial here is z cubed minus 11z plus 20. Remember the question here said factorize over the real numbers. So we can just use algebra factor, and we want to factorize that, comma z. We know the quadratic because we knew 2 minus I and 2 plus I, and now we have z equals minus 4 is a real root. A bit of interpretation on the Argand diagram. We are given the equation 1 on z plus 1 on z conjugate is 1, and we wish to see what sort of locus it is for any values of z. So we'll start with the calculator screen again, and because I have different problems, I will define z is again x plus y multiplied times I. And once I've done that, I can enter my equation, which was 1 over z plus another fraction 1 over conjugate of z, close the bracket, and all that was equal to 1. So it tells me that the Cartesian relation is given by this. This form is not nice to use, so I will multiply everything by x squared plus y squared, which gives me this equation. Looks like a circle, so I can go algebra and I can complete the square for x and for y, which gives me, if I multiply times minus 1, x minus 1 squared plus y squared equals minus 1. So I can get the equation of the circle here. But I can also copy this and open a graph screen and change graph entry to relation and just Control-V paste it. And I can clearly see it is a circle. How do I get the radius? Analyze graph, analyze conics. Radius is 1. And then if I repeat that again, menu, analyze conics, I can get the center. So that's another way I can display my locus of all the points, which is the circle with center and 1, 0, and radius 1. So you can do it algebraically, but to complete the square, you need to have it in a better form, or you can draw it using relations and use analyze conics. Find all solutions of the equation z to the power 4 is minus 1 and give your answer in modulus argument form. So that can be done in two different ways. I can use C-solve, and because my calculator at the moment is in real setting, my answers will be Cartesian. That's how the calculator will display it. So let's try this first. C-solve, menu algebra, we go to complex numbers and we do C-solve, and the equation is z to the power 4 is equal to -1. And we are solving for z. So as I said, we'll get 4 solutions according to the fundamental theorem of algebra. We know that any polynomial of degree n will have n solutions. The coefficients are real, so we can see that solutions occur in conjugate pairs. But if I want polar answers, I go to menu, number, complex numbers tools, and convert to polar. So the calculator now displays, it's 1 cis pi on 4, 1 cis minus pi on 4, 1 cis 3 pi on 4, and 1 cis minus 3 pi on 4. As we see, they do occur in conjugate pairs as explained. The other way of doing it, I could, in document settings, change to polar for this particular exercise. And now if I go up and I bring this down, it will solve in polar as long as I'm in radians. So let's try that again. And then we just get the answer. So you could see here the difference between being in degrees and radians. Degrees, it will give you the answers in degrees, but for complex numbers, of course, we require to have the answers in radians. The complex number 2 plus 4i is one of the roots to the quadratic equation, x squared plus bx plus c is 0, where b and c are real numbers. Find b and c. So how would we do that? If 2 plus 4i is one of the roots, 2 minus 4i is another one, because the quadratic has real coefficients. So this time we'll use menu algebra expand, and I need another bracket here, and I go z minus 2 minus 4i is my first root, and I close the bracket, and I multiply that by z minus 2 plus 4i, and the calculator expands it for me. So it's z squared minus 4z plus 20, which means that b is minus 4 and c is 20. If you are told, in addition, let's say that we have 2 plus 4i is one of the roots, and 2 is a real root, and I is one of the other roots, so we can now obtain a polynomial of the 5th degree if we go algebra expand, and I will have another bracket here, plus put this quadratic in, and then I would multiply times z minus 2, because as I said, let's say z equals to 2 is another root, times z minus I, close the bracket, and it's a good habit to have times between brackets, otherwise sometimes it doesn't work, z plus I, and then I get the polynomial of the 5th degree, with real coefficients and roots. 2 plus for I, 2 minus for I, real root 2, z is I and z is minus I, 2 complex roots. That brings us to a typical exam question. Given that P in Z is a polynomial of degree n with real coefficients, and Z equals to 2 minus 1i and Z equals 3i, I have 3 roots, then the smallest possible value of n is. So again, we are given 1 real root and 2 complex roots, but complex roots need to occur in conjugate pairs because of the real coefficients. So we will have 2 minus I, 2 plus I, 2, 3i minus 3i and 2, 4, and z equals 2. So the smallest degree of the polynomial will be 5. So these are all the questions, examples I prepared for today's webinar. You also have a student handout with more questions which you can practice after this session and see if you can follow what we've learned. If not, there are clear instructions how to do it. I hope you enjoyed this session and it was a good revision for you. Thank you.